Today we'll look at something called gravitational torque and something called the center of gravity. Gravitational torque is the name that your textbook gives to this chapter. It's a little grandiose for what's going on here. Gravitational torque is just torque due to gravity. We've talked about how to compute the torque due to a force acting at a single point. But a real object is made of lots of atoms, and gravity acts on each one. So imagine if we had, say a meter stick, which we're going to pivot here, but really the meter stick is made of a bunch of different atoms. Well, a lot of different atoms, and each one of them would have their own little gravitational force, and therefore their own little gravitational torque. It would seem that computing the gravitational torque would be tedious at best and impossible at worst, but in fact it's pretty simple for the following reason. Every object has a special point called its center of gravity. For the purpose of gravitational torque, we can act as if the entire weight of the object is acting at the center of gravity. Over here we have the diagrammatic symbol for center of gravity. This is pretty traditional. Since the motion of the center of gravity tells about the forces and torques, you often see this symbol on, say, crash test dummies. All right, the center of gravity is at the cross here, where these two things cross, and then the checkerboard pattern allows that if it rotates, it's pretty easy to measure that rotation. Note that something suspended at or directly above its center of gravity will have no net torque on it, since the weight's line of action will pass through the pivot and have a moment arm of 0. Such an object would not spin under the influence of gravity. An object or collection of objects is in balance when its center of mass is directly above or directly below the point of support. In such case, the force of gravity passes through the pivot point and has a moment arm of 0. Therefore, gravity will exert no torque and the object will remain balanced. That means that, for instance, here we can tell that the center of gravity must be somewhere along this vertical line. It's probably about here, but somewhere on that vertical line so that there would be no torque. If instead the center of gravity had been over here, for instance, then the moment arm would be this. There would be a gravitational force acting downward, and there'd be a torque that produced a rotation like this, and of course it would fall. Here we have a piece of artwork that my wife brought back from Ghana, I think from Ghana, which is a bunch of plaques connected by chain link, and in one of our many moves, one of the links broke. The object then becomes two connected objects, and they each move until their center of mass is below their hanging point. So we can see on the top guy, the center of mass would be more or less at the center of the crosses pointing out there, the boxes that have been out there, and we can see that that's pretty close directly below. You might say, well, Mr. Lockhart-Gilroy, look, it's not directly below, but there's a bit of a cheat. We'll see that the fact that there's mass missing here means that the center of mass should have been a little bit lower than the symmetry. Should have been shifted a little bit towards the bottom. And likewise with this one, where again I've drawn sort of the X that makes the center of the thing, which is pretty close to right, because if you look, there's a lot of symmetry here. So that's probably pretty close to center of mass, and it is directly below the pivot point, which you can see there. How to compute the location of the center of gravity. If we have a pair of point masses, M1 and M2, and they're located at actual positions X1 and X2, but they're point-like, so that's exactly where they are, the center of gravity is at their mass-weighted average position. This is a terrible confluence of terms in statistics and physics. So position is a physics term, yay, make that, and we're taking their average position where they tend to be, but it's a weighted average, meaning it's not everybody just by adding up their positions and divided by the number you have, but you make each new position carry some weight that's different, and what makes it different is their mass. The problem here is that this is a conflict, a collision between physics and stat terms. This weight is not the physical weight, it's the statistical weight. Don't worry about that too much, but if it bothers you, let yourself know. It is a little awkward. It's a little bit unfortunate the way it was set up. The actual formula, though, is really, really very, very easy. The center of gravity position is M1 X1 plus M2 X2 all over M1 plus M2. In other words, the mass times the position of each one added up over just the masses added up. You derive this from the fact that if the dumbbell is pivoted at that center of gravity, it would not rotate. And you can probably see how that kind of works out, that these two things are being balanced. If there are more than two objects, we find it in a similar manner. We just say the center of gravity is each mass times each position that the mass is at, all summed up divided by the total mass. If the object can move in 2 or 3 dimensions, then you might have to do the same for the y and even for the z coordinates, but the formula would be the same. You just replace every x with a y or with a z. There's a variant that I like better, but it's algebraically identical, so you don't have to actually remember it. I like saying the total mass in the system times the center of gravity of the system is equal to the sum of each mass times its own position. So everybody has the same form here. In all cases, though, note that the center of gravity tends to be near the heavier objects. You can certainly move it other places by taking great separations between light and heavy objects or having a collection of light objects, but it tends to be closer to the heavier part of the system. All right, a 1 meter long dumbbell has a 10 kilogram mass on the left end and a 5 kilogram mass on the right. Find the position of the center of gravity, which is the point where the dumbbell should be lifted in order to remain balanced. The assumption here is the dumbbell is itself massless. So, as always in physics, let's draw our picture. This is 10, this is 5. This distance is 1 meter. They tell us answer in meters, but measured from the 10 kilogram mass. So this position is also the origin. Wow. Which means this position must be 1 meter. And we have that the total mass, 10 kilograms plus 5 kilograms, times the center of mass position, center of gravity position, is 10 kilograms times 0 meters plus 5 kilograms times 1 meter, or 15 kilograms times the center of gravity position is 5 kilogram meters. The center of gravity must be at 1/3 meter over from the 10 kilogram mass, so this is 1/3 meter. Which point could be the center of gravity of this L-shaped piece? Assume the bar is uniform. Here we might want to think of it this way. If we had cut off this, then B is the center of this blue region. But there's some extra mass to the right, so the center of gravity of the whole thing has to be somewhere to the right. So it must be D or A or C, but it can't be B. If I do the same kind of thing, and I slice off here, D is the center of that one. But again, there's some mass below, and so it must be A, B, or C. It can't be A, so no, it can't be B. We've already eliminated B, so it's A or C. And then we look and say, well, again, if there had been no mass here at all, then in the top part, then this would have been the center of gravity. There's more mass above than below that central line, so it must be A. These balls are connected by light rods pivoted at the point indicated by a dot and the letter P. The rod lengths are all equal except for A, which is twice as long. Circle in blue the letters with the greatest magnitude of the gravitational force, and circle in red the letters with the least. I'm just going to call that L, so we have something. And I'm going to call these things what I called M. All right. So let's just actually compute the net torques. This one has a torque mgl, and this exerts a torque m2m times gl, but they're in opposite directions, so the net here is mgl this way. Over here, let's go here. The m exerts no torque because it's at the pivot point. 2m exerts a torque, which is 2m times GL. Here we have that the 2m exerts no torque because it's at the pivot point, and we just get mgl. And down here we get mgl from this plus something else. It looks like it's at the halfway point, but it doesn't really matter. It's just something more than 0. Should put it this way. More than 0, but less than mgl. So we can see that this is going to be the greatest because 2 is the biggest, obviously. And these are going to be the least because D is going to fall between them. In both cases shown, a massless rod is supported by a fulcrum, and a 200-gram hanging mass suspended from the left end of the rod by some cable. A downward force F keeps the rods at rest. Each rod here is measured at 10 centimeter intervals, in which case is the magnitude of F larger. Just for completeness, because I don't like them using the same symbol, I'm going to call this F star, just so we can talk about it. And we can see that in the first case, F is going to be F times 3 lengths equals 200 times G times 1 length. So F is 200 thirds kilograms times G. And then you say over here, well, that's going to be a little harder because the moment arms are different. Right? We're going to say that's the line of action for that gravitational force. So I guess really we should go from here. This is the moment arm. And that's the line of action for our responding force. So this is the moment arm. And they're shorter than they were before. They're not 10 and 30 centimeters. But we can see that they're both short by the same factor, which is cosine of this angle. So we would have F star times 3L cos theta equals 200G times L cos theta. And the cos thetas will cancel out, so that F star is still 200 thirds kilograms times G. So we get that it's the same in both cases. A mobile made from 3 piggy banks, A, B, and C, is shown. The banks are identical, except they contain different numbers of coins and thus have differing masses. Which bank has the most coins? By the way, we have to be a little careful here because it would depend on if they had the same coins in them, right? Dimes are worth more, but weigh much less, and so on. So you'd have to more really say which ones have the higher mass, not which has the most coins. The key thing for all of this is that when two things are suspended from a pivot point on a massless thing like a rod, then the heavier object is closer in so that they can balance out, so the torques can be balanced. So we can see that C is more than B, since C is much closer than B. But if we then treat this as a black box, we can see that A is greater than the box because A's length is much less than the box's length, which means A is greater than either thing that's in there, so it's greater than C and it's greater than B. Our winner is A has the most.